So, good morning, everyone. Today we have Almudena from the house. Well, she was telling me about her CV before, and I was surprised to how many places she's worked in. She got her PhD degree from the Complutense in Madrid, but she's been a postdoc in Garching, in the Space Telescope European Coordination Facility. She's also worked in the Garching Max Planck for extraterrestrial physics, in the X-ray team for the PSPC camera for Rosat. She came back to the IAC, but then she left again to work as a staff in ISO for the coordinated operation of the infrared instruments for the VLT. She moved again to Heidelberg to work in the high spatial resolution studies of AGN, and now she's back to the IAC as a staff. And today she's going to talk about the spectral energy distribution of AGNs. So.
All right. Okay. So let me first introduce this study within the much larger project it belongs to, which is a should go with this. It's a project that we call an Institute parsec, which is aimed at the study of center of galaxies, regardless whether they are active or not, with very high spatial resolution. And we are focusing mostly on nearby galaxies. ¿This is normal? ¿Por qué apretar? The science driver behind is the we are looking at with very high spatial resolution, means the scales of parsecs. Center of galaxies means a scale of 1 kiloparsec or so. And we are trying to see features or characteristics that give us a hint on how activity can be set in the nucleus of a galaxy. So basically we try to look for material at the center, whether this material is available to feed the central source, and how this material, although might be available, if there is ways, or we can visualize directly whether this material can be get straight to the center. Technically, the project is much launched because of the possibility of getting very high spatial solution. No sé qué hacer. ¿Estás seguro? ¿Y qué hago? Very high spatial resolution in the infrared. This we can get routinely now since a few years. It's a resolution which is comparable to what we get in radio routinely and with the space telescope. And so why infrared? Well, because center of galaxies are usually very dusty regions. And so having high spatial resolution in the optical sometimes will help you much, because if you have a screen of dust in front, you won't be able to see very close to the center what is going on. While in the infrared, we can get through the dust, and we can see more precisely and much more in detail what happens. So if we, in addition, we get a high spatial resolution in this regime, well, this is the way to go to study these objects. Now, this high spatial resolution requires special techniques, and that means that it comes to a certain price. We cannot always observe our, I don't know what to do. It's true. Or disable, or what is the other option? Because if I had to find, yes, I'm okay. Well, okay, I will try not to go over there. Let's see. Oh, thanks, because now I get the point. So, okay, this comes to very high. I don't have to go to the corner right up. This comes with a certain price, as I say, because we need a special technique. We can now observe our favorite objects. So and we had to rely on observing very bright stars, very bright objects. So the study that now we are doing in parsec is getting reduced to very nearby in bright objects, and in the extragalactic field, the brightest objects are mostly aliens. So that is how it comes, this study. And what I'm going to present you, mostly based in active galactic nuclei, and because we are doing them from the VLT, most of the targets we are going to study come from the southern hemisphere. So, as I said, I'm going to show you a spectral distribution of the nearest, brightest aliens in the south sky. We are going to sample them with scales of 2-second scales from the UV all the way to radio, and the novelty here is that we can get the infrared at the similar scales as we see UV and radio. So it means that we are going to sample about the same physical region in all this spectral range, not the same physical process, but we are going to be consistent in terms of integrating emission from the same region in the nucleus of the galaxy. So here you see where I put it here in the typical resolution we are going to get in the near infrared, much below 10th of a second. In the mid infrared, we can get routinely diffraction luminosity of 8-meter telescope, so we can get a second. And only for the very, very bright ones, we have the privilege to enjoy interferometry at 10 microns, and then we can get really down. But this is very exclusive for only a few objects. I'm going to show you spectral distributions of two types of aliens. The big family of aliens are divided in two major classes, type 2 aliens, type 1 aliens. And you might have already heard what is the difference, but just very outlined for you. There is a lot of dust in central galaxies, so there are in alien as well. We need in this material, this dust close to the center to fuel the central source. And in type 2 sources, this dust or this material is located in such an unlucky way in our line of sight that it prevents us to see the nuclear emission of the galaxy, or the nuclear emission of the alien, in particular in the optical and UV. In type 1 objects, it's exactly the same as type 2. This is our view of how we can classify and understand aliens in these big two categories. Type 1 will be exactly the same as type 2, but we have a much more lucky view of the central engine because the dust is there, but it allows us to see closer to the center. So I'm going to show you these SEDs. For type 1 aliens, obscure aliens, I will refer in general to them like that, and for type 1 aliens, and a very high spatial resolution. And you will see, that will be the outline of my talk, that at this high resolution you can very nicely distinguish, very in a clean way, what is a type 2 source when you have a type 1 source. Okay, I will show also to you that when you try to do this distinction, if you use low-resolution data, and in particular if you use satellite data, you cannot do that. You cannot distinguish because the spectral distributions look very different, and they are quite measure the power of the alien much more than it should be. Okay, that will be the outline of the talk where I am. So here I put some of the objects we are looking at, just to give you a flavor. We are looking at very famous objects. We go for closest objects in the sky, like Centaurus A, and most of the sample is located at distance around Virgo. And we have further objects. We get up to 3273. This is quite exceptionally. It's too far. It's actually the only quasar we have in the sample, but it was bright, it was easy to do, so we can make it. But most of them, we are moderated distance to profit of the spatial resolution. Here you have what is 1 second in these objects in parsec. So you divide this number by 10, you get an idea what is the typical spatial resolution we can get in the infrared. And here gives you the size of the core of these aliens in parsecs at 2 microns. So this number here tells you at which scale we are going to sample the spectral energy distributions that I'm going to show you now. You see, we are sampled these regions in the range of few parsecs, typically on the range of few tens of a parsec. Okay, before showing you the spectral distribution, I want to make it two remarks. The first one relates to the obscure agents. As I said, the obscure agents, the type 2 agents, are those that the dust prevent us to see a direct view of the central nucleus, in particular in the optical. So you have here, I put 3 examples of 3 nearby galaxies. The upper row is space telescope images and the optical, and the lower row are infrared images at 2 microns. So, very annoying. So when you go to when you try to see the nucleus of this galaxy in the optical, you don't see it. It's completely obscure. But in the infrared, these objects come immediately. They come as the most outstanding source in the infrared. And in some cases, this is the bright sources you see here in the panel below. Okay, the red point here, the bright source here. Actually, it's the most important source. You see in the infrared, not much from the galaxy, but definitely you are unmistakable. You detect the bright source, the nucleus. In some cases, we have some other sources in the field, and we can do very good astrometry, precisely locate the position of the infrared nucleus, and then go back to the optical images to see whether there is a counterpart in the optical. And we found that in many cases when we can do that, there is no optical counterpart. I say there are observed sources, but it means that we cannot measure anything, usually from 1 micron on, so these are just 1 micron short wave. You can measure nothing. So this means that we cannot get information of these nuclei in the optical and the UV. So we will have a huge data gap in the SED, in the spectral distribution, which we cannot feel because the object is completely obscure. And you will see how this affects the spectral distributions. Está siendo complicado. So the other remark I want to make is about agents coming in 2 different flavors. There are there are what I call the very powerful agents. These agents dominate the light of the galaxy. Okay, the contribution from the nucleus itself dominates the light of the galaxy. And this is the case of a quasar, and I put here 2 examples. Quasar 3273, which is the most powerful quasar in the sky, and of course is dominated by, I don't know why. Dominates the light of the galaxy. Here you have an example of a type 2 source, so an absorber alien, and you can realize immediately from the image that the nucleus is the most outstanding source in this galaxy. It behaves exactly like it were like a quasar, like the object is nest, but it's much less powerful. It's a million powerful alien. It's a super galaxy. So in these objects, doesn't matter what kind of aperture you use to measure the emission from the center, because the emission is dominated mostly from the alien. But this is exceptional, and most of the objects come in this second flavor. Okay, and I put here as an example of well-known objects. And this is a type 2, 1068. 1068. Centaurus A, a type 1 source, 1516, and Delphinus. And in these objects, it really matters. These objects are very modest aliens because here the light from the alien represents a very tiny fraction of the total light of the galaxy. You will see that this also has an implication in the spectral distributions. So here I show you finally the spectral distribution, or some of them. This is an example. Let's see what we have here. We have, I choose more or less a spectral distribution of every type. We have a type 2 AEN, 1068, very famous, a Centaurus A, it's a radio galaxy, also type 2. A type 1 galaxy, NGC 156, sorry. And a liner. Liners are low power aliens, okay? And let's see what we have plotted. The scales are the same in all the plots, so I'm going to display only just looking at 1068. We are plotting here in the x-axis Earth's frequency, and in the y-axis we are plotting a power, nu epsilon. Okay? And what the range we are covering is the right part we get the X-rays, high energy. Then we have a data gap here. Part of this data gap is related to the extreme UVs of X-rays. This is a region of the spectrum we cannot observe. It's inaccessible. And this is a type 2. So the gap is much wider it should be because, as I said before, this object is absorbed, the emission in the UV in the optical is absorbed by that, so we do not see any information in the optical that should be in this region. And the first data point we can plot it, and it's an upper limit, is about 1 micron. Is the upper limit detection of the nucleus of this source. At the shortest wavelength we can go. But then this nucleus becomes very powerful immediately as you go to the infrared, and then it forms this type of bump with have a maximum around 2 microns, a sort of plateau in the 10, 20 microns. And at 20 microns is the last data point we can plot in these SEDs in all the objects, because it's the last data point at which we can get relatively high spatial resolution comparable to the rest. So therefore we have a huge data gap here, which includes near infrared and millimetric region. We cannot put any data. And then we go to the radio, which is just the left part, recovered against the nuclear emission. Okay? So this bump in 1068 that we see in the infrared, while repeats better sample in Centaurus A as well, is what you have here in this liner 2. And and then in 156 as well. This is a type 1 object, so let's compare a type 2 with a type 1 object. We have also the bump, this infrared bump here, but instead of falling down dramatically as it falls in the infrared, it recovers in the around 1 micron 2. Okay, and it forms this bump. This is the blue bump, the characteristic blue bump we measure in quasar, and we believe is due to emission from the accretion disk. Okay, so in Taiwan we should see that because, as I said before, we have a clean view of the central alien. Otherwise, the rest of the SEDs are the rest of the spectral distribution, better or less sample, is very similar in all cases. So what happened if I try to fill up this gap in the mid-infrared and far-infrared with the only thing we have, satellite data, okay? Okay, so this is what it comes from. It's the same plots as before. The only thing now is that I add with crosses data from satellites, okay? And you can see now that these crosses that represent low resolution data do not follow the trend defined by the high-resolution data, okay? They follow a completely different trend, so they are not tracing the AEN, and even more, they are not only not tracing the AEN in shape, but they are also shifted in power. There are orders of magnitude difference between the power that you might measure from the high-resolution data from these SEDs compared to what you will measure from this low-resolution data from the satellites. Okay, this is most of the cases, but I have told you before that other AENs exceptionally, which is just the opposite. And this I put the three examples, a quasar, a type 1 object, a type 2. And again, the black points are the high-resolution data, and also here the crosses are included, satellite data. And you see that in these cases, the crosses follow nicely the spectral distribution of the high-resolution data. So in these cases, it doesn't matter what aperture you use, what kind of, you don't need high spatial resolutions. I mean, you are not learning nothing new for high spatial resolution information. You have all that in low-resolution data. These objects, despite of being, for example, including a type 2 source or a type 1 source, these are medium power sources. As we can see from the spectral distribution, they behave exactly like the quasars that are available.
So if you make the factor correction of the flux, it doesn't follow the shape?
Sorry, wait. I made the factor correct. No sé qué hacer. It's very annoying, that. Sure. Tell me, I didn't make any factor correction.
No. So I mean, so you say that the new crosses doesn't follow the same trend, but if you just simply scale down, it doesn't follow what you expect. It's not the same that the AEN.
But this is why should I scale down?
No, you should not. But I mean, you said if I understand you well, that they don't follow the same trend. So it's not just a simply matter of a factor?
Or a scaling factor. It could be, but look, for example, Centaurus A, no? It's going up, and Centaurus A going down. Look at 1097, no? The right down. No, it follows a trend that is a bit different than what you might imply from the low resolution. In general, these are examples, but in general you might have, end up to have a sort of plateau in the high resolution data. No, that is the point. That is the point. We are not probing the same region. The point is that up to now, when we had an AEN, and even now, people are resorting to satellite data because there is nothing else to trace the AEN. What I'm showing to you is that when you do that, you trace the galaxy. You do not trace the AEN. And it's not just small factor, it's orders of magnitude. So it could be what you say, maybe you scale down, maybe, but well, we are 2 orders of magnitude in the scaling sometimes. Okay, but other cases, as I say, exceptionally there are cases which is not the case, so it's fine. Now, here I wanted to emphasize a little bit more. This is again to SEDs of high-resolution data, the black points. And what I put it here on top is what we have today as a template or a Cipher-2 galaxy. Right? This template is made by Marie Poulette and collaborators. They are putting Cipher-2 galaxies and making this average, relying on low-resolution data. I scale this template, which is the red line, to the crosses that are there, because the crosses are satellite, and they use satellite data too. So we are using the same information, the same data. So I think I am entitled to do this scaling there. And it's just not just to measure. This is, to do this, you don't have to try to measure any power here. You simply have to see at the shape. You see that the shape is just even the opposite. It's no, this template of the Cipher-2 does not keep any record or being an AEN being inside. And there are AENs, because we know we have put the AENs to make it. It gives no record, no information of having an AEN inside. So this is a warning because you use this template for modeling or for subtracting the AGN component or for comparison with surveys on medium high ratio. You might make a gross mistake because you are not seeing the AGN. Now, this is a little bit to see where we can identify what these infrared SEDs come from. Of course, it might have to come from the galaxy. We were just wondering whether, because we are systematically classifying these objects with a lot of infrared emission as AGNs, whether it could be that we are systematically also, for example, a strong star formation around the center, which is contributing to these infrared SEDs we see. So these are diffraction-limited images, okay, at 20 microns. It's the longest wavelength we can look at this. And with certain resolution, with certain spatial resolution, and of some of the objects we are studying. And you see that at 20 microns we are dominated by a central point source. This is the brightest source. And in some cases, yes, it definitely will have some diffuse emission, like here in 1068, or definitely we have a lot of diffuse emission. And 13, sometimes it's just simply a point source. So in my opinion, this infrared SEDs, which is enormous, might have to come from the galaxy, from the complete galaxy as a body, and probably come from some diffuse emission across the galaxy. In some cases, it's true. We see a lot of very strong star formation around. Okay, these are examples, and this star formation could be as important as the central source, as the AGN itself. Okay, so this tells us that when we measure in satellite data, we include the AGN, and obviously we include in something which is not the AGN, and somehow more or less we get what we are measuring with the satellite data. Okay, so let's back to the high resolution SEDs. I showed you a few examples, and now let's try to make a template, a best genuine representation of a spectral distribution or AGN based on high resolution data. So we are going to average some of the best representative type 2 objects we have, and I put it here. Some of them we are taking at different colors. The red line is the average. The same scale as before, okay, X-rays, the usual gap, the infrared, the radio here. I make an extrapolation or interpolation here, which might be arguable. I'm not in principle entitled to do that, because as you can see, I have no data doing that. And for type 1s as well, we have also an infrared bump, the usual blue bump. The red line is the average, so let's put them, make this average. You can see with this comparison that the SEDs do not differ much. Within each group, they don't differ much, so we are not doing so bad job, although the study is small. Okay, this is what it comes from comparing, putting just simply one on top of the other. The red will be the spectral distribution for a type 2 object, an absorbed source, and the blue for a type 1 object. Okay, so now we have, you can see we have two major features here. We have the high energies here, both type 1 and type 2 showing an increasing trend in power. We don't know, unfortunately, what happened at further energies. We can get data to 100 kV and not sensitive enough to get any further, unfortunately, but it's quite suggestive, this trend, by the way. Then we have the usual unavoidable gap here, information. And then we have the big, this strong, relatively narrow, much narrower than was assumed before for AGNs, narrow infrared bump, which is common for type 1 and type 2, which tell us that we have a lot of that in both cases, either in type 1 as in type 2, obviously. These bumps are very well reconciled with our black body spectrum, so we can assume that it's really dust, or most probably it's dust that's emitting the light from probably the accretion disk. UV, optical emission, is absorbed by this material very close to the center. Remember, we are at a distance of a few parsecs now in these SEDs, and putting back in the infrared, and it's doing that for type 1 and type 2 objects. And type 2 objects, as we already saw in individual cases, the emission drops dramatically. The infrared bump goes sharply down because the source is not detected. But in type 1 objects, is not the case. We can see the source, and indeed, as I say, the dust is distributed in a way we can see to the nucleus, but also we can see the hottest dust. Okay, we are assuming we have a lot of material. This material is located at different radius, and the one is closer to the center will be hotter, and the one closer, farther away will be colder. We are sampling here in the SED the bulk of the dust are intermediate temperatures, but this widening of the spectral distribution for type 1 objects is simply emission from the hotter disk. We can see the nucleus, but also we can see the hotter disk. This is the feature, the characteristic feature of that. Otherwise, we have as extrapolation, which, as I said, can be arguable, we have similar shape from the infrared bump and from the mid-infrared towards the radium. Okay? This blue bump, if you allow me to go back, compared with a quasar, I told you of 3273, the brightest quasar in the sky, is the yellow line here. Okay? This is a higher rank AN. Most of the galaxies we are putting here are medium power ANs. Okay? And you might see that they have, of course, as a quasar has a blue bump. This is emission from the accretion disk. And in comparison to our cities, this blue bump is much more tiny. So, on the contrary, you might see that the infrared is almost flat. We don't have an infrared bump, while we have in the super galaxies we have. So this probably is an effect of dust. We might have destroyed completely all the dust in 3273. So we have nothing to absorb, and everything we see is in the accretion disk, directly in the accretion disk, what we measure. What we are not seeing here, it should be here in type 1 objects. We see back in the infrared. It's reabsorbed and back re-emitted in the infrared. So, when making this average template, now the next thing, since we have a genuine or a better representation, a better template of what could be an AEN, the idea will be, let's see how much power intrinsically we have in these objects. So let's integrate the spectral distribution. You might immediately see that most of the energy integrated in the spectrum will come essentially from the infrared bump. So the infrared bump, we are not able to measure very well the blue bump because a lot of dust is absorbing it, but it doesn't matter because this is getting back from the infrared, so indirectly we get a good proxy of the total power of the source by measurement. And that is what I wanted to show you in this table. It's just putting a bit numbers to give you a feeling. These are some of the galaxies. I just saw SEDs, some of them. Others are new here in this table. This is the power integrated in this infrared band. I sorted these objects, by the way, in increasing power. The lower power sources are at the top. Increasing power goes down. So you see, we are different scales in luminosity, although this is a bit outlier because 3273 gets too far away in luminosity with respect to the average sample. No? As I said. Here you have a comparison of what you will determine by summing, integrating the spectral distribution on the base of low resolution data and compared to the real spectral distribution of this AEN. So you see that already here you see the orders of magnitude SEDs you might introduce if you rely on large aperture data, in particular on satellite data. And here is what I was telling you. You compare, you try to integrate the total energy from this SED compared with what is stored in the core. The core carries most of the power. So basically, in most cases, not always, there are exceptions here, and the statistics we are not having. We can add a few more objects, but not many, unfortunately. But in general, this infrared core carries almost 90% or at least more than half, definitely, of the total energy we measure in this source. It's a good estimate if we measure in this course. If we end up to have this very well determination of the infrared core, it's a good way to measure that, to infer about the total power of the AEM. Okay, and that is the summary. I'm finished. I just wanted to get back to tools that are been using since the time of IVAS, which is the use of colors to discriminate AEMs for normal galaxies. This is continually doing now, using other infrared information. And I must say it has been in general successful, but it's surprising that success because of what I just told you now. Because the SEDs in general from large aperture differ quite a lot in shape, in my opinion, from those derived from the high resolution data, and because the infrared satellite data also overestimates substantially the luminosity of the core. This infrared excess we might try to pinpoint to another sources which are not the AEM, and I believe that probably is this huge space might be associated with sort of diffuse emission across the galaxy, across the whole body of the galaxy, but definitely nothing to do with the AEM or with the star formation or with maybe H2 regions in the spiral arms of this galaxy. These are huge objects. And we have made better templates of what is an AEM core, and found out that there is the major feature, which is the infrared band. The second feature is the index rays, an increasing trend in power with energy. But the major feature is the infrared band, and this carries most of the energy of the AEM. So if you measure there, you get a good estimate of the total power. And yes, thanks for coming.
Questions?
So, can you go back to the slide where you saw the two average SEDs of the AEMs?
The two?
Average.
Ah.
So my question is, yeah, that one. So it is possible to represent with the physical model what is going on there? What is the source of energy that is producing this SED? Is, for example, something that can be a star cluster at the center of the galaxy hidden by dust, or it cannot be represented by that model? So you need, for example, like the black hole emitting, so hitting the dust. And so I just wonder whether there is any theoretical model on the literature that can explain the feature that you see there.
This feature, well, this is, I mean, this temperature it is now, no. We can interpret, I try to give you an interpretation intuitively, then within the scenario we understand AEMs. Go with a model to try that. Actually, as I say, we have done that for a couple of objects. And but within the framework of considering that we have an AEM at the center, you have to explain different physical processes that happen here. Because in radio you have mostly synchrotron emission, but you might have thermal emission as well, because you have Prieto. The infrared you have mostly dust, and this bump can be explained by possible torus models that are plenty in the literature, although the current ones are not going to explain that because they are much broader than what we are seeing now, so they had to be refined. And the accretion, this blue bump, well, it's just also a thermal model. So you can explain all together if you rely on the standard AEM scenario, a black hole, accretion disk, and a torus. If you do that, we have done for two objects, and it works, it's fine, it's okay. And the presence of that is fundamental, because actually all this feature is just dominated basically by the effect of dust. It's like it's in an extinction curve, if you want. Now, if you put clusters, it's a bit difficult.
The blue excess that you see when you go in the average S1, when you go to the optical, this excess in emission is not explained by star emission, so it's not something like a star cluster at the center of the galaxy. Because you are less dominated by dust there, no? So in principle, you would expect to be dominated in the optical by star emission. So that's my
yes. The point is that if you go to the shape, or I could have done that. If you go to the shape of a young stellar cluster, it's not going, depending on the age, it's not going to go in that way. You have to realize, I mean, it has to be very young, but then you end up in another problem, that stars do not hit the dust that hot as we see here. The blue band, I should have shown here to you how a giant stellar cluster spectral distribution look like, but it's not like that. This is really a band in the UV, and it's not like that.
More questions?
If you could go to the previous slide, meaning where you actually create the average SED there. I understand that the quasar spectral energy distribution is just shown as a comparison. It has nothing to do with creating the template. Is it correct?
No, we didn't include it in the template. No.
All right.
No, sure.
And the thing that puzzles me is in the X-ray end. I mean, the X-ray spectral energy distribution has an enormous spread in orders of magnitude.
Mm-hmm.
So I can vaguely understand that there is a trend, but how reliable that trend is, how much would you bet that that has some real meaning in your interpretation and everything?
Yes. What can I tell you? I mean, there are two problems in the X-rays. The first problem is the soft X-rays, which would be a standard emission. They're included there. I include there for consistency. If I were correct, I should not include it because, of course, in X-rays we don't have resolution, right? I'm assuming that X-rays are mostly produced at the central engine, but this is an ad hoc assumption. So soft X-rays I should not have included there. But because there was the general trend increasing in power, and this increasing in power systematically appeared from 60 kV or so, and there, as I am most probably dominated by the AGN, I tend to believe that the simply increasing trend in power with energy is reliable. And it follows nicely in Type 1 objects, although the spread in power. It follows like the quasar, it's another AGN, but more powerful. It follows less in Type 2 objects, but most of the sources are here are quantum thick. So if they are quantum thick, you have column density 10 to the 24. This is a killer even also in the X-ray. So it might spread a little bit of the scatter, although not completely, because 60 or 100 kV should not be. So I think there is a trend. Just leave it like that. And ideally will be to be able to detect these sources at higher energy, because I believe that maybe we get a surprise and have another stronger band over there.
If you don't mind, Chairwoman, I have another question. What's the future? Well, this is basically related to what Nacho was asking. What's the future of your template? I understand that the template gives you a qualitative image of what's going on, a bit of hand waving here and there. Are you planning on having a more physically consistent follow-up work on it?
We are trying to, well, first of all, we need a little bit more statistics, so we had to do, which means adding a few more objects. We don't have many to settle better the SEDs. And when we try to do is verify whether the standard LGN scenario plays. In reality, can be fixed by these models, in the sense that we have the equation disk, and we have to have emission from the blue band, and we have to have a lot of dust, and this amount of dust should be equivalent whether we have Type 1 or Type 2. This is the unification of the AGN scenario. This is what we want to see. But also consider the radio, because the radio is an important contribution of an AGN, and with the radio we can account as well from the X-rays with inverse quantum emission. So we want to put all the physical processes happening together, whether we can get this.
Yeah, I just want to comment on your sentence about the use of satellite data. I mean, I think you are too pessimistic. I have done myself an exercise comparison point extracted from the satellite data from ISOCAM data, and compared with your data, and they are very similar. They are not far by any order of magnitude, but they are very similar. It's much more difficult. But yeah, I think satellites are very costly, and you shouldn't be so pessimistic. I think if you do a proper analysis, you can extract proper information. It's not simply have the point. Okay, if you have the point, including the whole galaxy, certainly you will have a lot of emission. But if you extract the nucleus, you can have more sensitive data than from there. I mean, the difference is huge. If you have the total emission from IRIS, for instance, or if you use image like ISOCAM or Spectral data, I think that's more, reliable.
Yeah, you have to assume models. I mean, yes, you can extract emission from the center, but you have to assume models. If you really can rely on the model you put, and you come to this, then you are okay. I think it's not the way around. If you can, maybe it can be done in that way, or can be used in that way. If I put the right models and I get back from...
The only model I assume is that the center you have a unresolved nucleus, so a PSF. And PSF from satellites are very stable, so easy to model, relatively easy to model.
The thing is that, again, I think that this, but I will be careful. I think this might work because there are cases definitely that the alien is so important. The PSF in the satellites is very huge. You cannot see better than inside the PSF. So if you have an alien that is really powerful and you define and there is a threshold in the scale which in that region on the alien dominates, you are done. Then you are done. It will be nice to find this threshold. What is the right scale at which these so modest aliens can overcome the light of the galaxy. So otherwise we are here.
So as you know, there is the effect of AGN on galaxy evolution, and this is responsible of stopping the formation of stars and so on. So I don't know whether this is it can be done with the data right now, but if where possible, I think it would be a nice idea to explore, which is if you take the full galaxy SED, something that you can do right now, and you remove the emission from the AGN that you have, and you compare the remaining SED and compare that ACD that should represent the stars from the galaxy with the same SED of normal galaxy without AGN, to see what is the physical effect of AGN on the star formation and so on. So I don't know whether this is feasible or not, but it's possible.
Yeah, no, I'm thinking it's one of the things in my head. To see what is the leftover. I mean, do the other way around. Yes, we can do that. We can do that only in the near, yeah, with too much. For example, we can do that. Yeah, no, yes.
More questions? So let's thank Almudena again.